we just evaluate it. But I would like to give you the expression of K1 and K12, K21 and K22. Expression K11 is negative of 1 plus cosine K1 L over 2. And K12 is 1 minus cosine K1 L over 2. For K21 is a little bit complicated. K21 is a bit, let's see, 2 square root of 2 over 2 times sine K1 L over 2 times sine, that's K2 L over 2 plus comes the cosine part for K2. Cosine K2 times L over 2. And for K22, you just reverse all these coefficients by the sine and cosine. So the square root of 2 over 2 times the sine K1 L over 2 times sine K2 L over 2 minus cosine K2 L over 2. So the only thing I have to be careful is just this. Okay, of course, let's not forget about the parentheses here. Okay, now how do we solve this? And the way to really solve this is to solve for the values of K1 L over 2, because right now the variables become these, K1 L over 2 and K2 L over 2. That becomes the principal variables, right? We are basically solving for this. However, they actually are not two different variables. Remember we found the relationship between K1 and K2, right? So how is K1 and K2 related? Anybody remember?
Square root of 2.
Yes, square root of 2. That means K1 is what? Square root of 2 times K2. So the whole thing is actually just K1 dependent, correct? Now, because of that, then you can just solve it. However, even that, we have a not so pretty mathematical expression involving the first order effect of sine and cosine and the second order of double sine in this case, which means that it's not that easy to be solved by hand. So there are different ways to do it, and I'm just giving a big picture. In the future, if you encounter this kind of problems on the FPE exam, how are you going to solve it? The first approach 1 is what we call theoretical. Theoretical derivation. In this approach, you will have to use this technique, what we call Taylor's expansion. And I will show you a few examples in the future. For this case, we're not going to do it because it's a little bit complicated. It's not that difficult, but it's just lengthy. Approach 2 is we can use numerical method. What is numerical method? Numerical method, despite the name, sounds very knowledgeable, and let's not get pedantic here. It's simply by plugging in different trial values of K1. You see that which one will actually meet your condition. What's the condition? The condition is here. This is the condition, which is this condition. Because in this expression, it's basically K1 dependent, right? The whole thing is just a K1 function. We don't know what a K1 is. What we can do is just try different values of K1 from 0 to, I don't know, 100. when you find out that the function's value becomes 0, which is right here, that means the value of K1 is the root of this equation. That is the fundamental spirit in numerical method. Today, you have the tremendous help from computers. And your computer is so fast, so quick, you can just solve this problem in seconds. And that's how I did it with this example. So I found that the values of K1 over 2, so numerically, I found that K1 L over 2, the first root is 1.0167. You just treat the whole thing as a variable. Then you can just plug in this value, and the first root is this. Now, because of this is this. So K2 times L over 2 is just the square root times this 1.0167. Which becomes what? About, is that right? Right? No, it's not right, right? K2 is 1 over, correct? Not multiply. It's 1 over square root of 2, because K1 is greater than K2, correct? So here, how do we correct it? It's very simple. You're going to love this kind of techniques. To correct it, you just put -1. Then you can flip it. I always do this. And so this is basically 1.0167 divided by square root of 2. It turns out to be 0.7189. Now, what's the critical load in this case? The critical load in this case is simply by recognizing the fact that we can go either K1 or K2. Now, K2 is easier because K2 is only P dependent. K1 is 2P dependent. So mathematically, you probably will consider both them equally easy. But if I go after K2, I said because K2 is the square root of P over EI, right? And you already know the value of K2 times L over 2. So you might have this expression, which is to say that K2 is just whatever the value you have at this point, 7189. So you can say 2 times 0.7189 divided by L. This whole thing equals to the square root of P over EI. Right? So what I did was just move all these terms from here to here. That's all I did. And once you arrive at this expression, of course, you can find the values of P, correct? You just move terms around. So from here.
Professor, it should be 0.7189 there, not 0.7181.
Thank you very much. Good catch. And this means PCR is what? The numerical value of PCR is 2.067, something like that, times EI divided by L squared. Right? Now we have found the critical load of this problem. That means we finally solved it. This is the critical load of the column. Now let's use the concept of effective length factor. How do we calculate the effective length factor here? How do we find that? If you remember, effective length factor, capital K, equals what? How do we determine that? K equals the square root of PE divided by PCR. Remember? By definition. Right? By definition is this. Now, mathematically, how do you do that? Well, piece of advice, don't plug in the whole thing into here. Because you remember that what's PE? PE is just pi squared EI over L squared. This is PE, right? You recognize that they both share EI over L squared. So when you do the math, just drop EI over L squared out. That means what you have to do is just simply pay attention to what? To these two parts. One is this, the other is this. When you calculate the effective length factor, what you have to do is just do this. Square root of, for the PE, just take pi squared. What about PCR? Just take 2.067 here. Then we'll give you very nicely this number to be 2.1853. And there, we have found effective length factor for this column as well, which is a bonus. Even the problem did not ask us to do it, but let's practice the concept that we introduced before. Any questions? Clear? Okay, all right. As long as it's clear. All right, now the next topic I'd like to talk about is, let me see my notes. Now, next I would like to talk about example of different approaches, the second order and the fourth order approach of differential equations. So for that, we're going to go back to my slides, and that is the column one, which is this, but it is this one. To this important, well, when I say important, everything is important, isn't it? Talk about the different approaches. And this is what I call second order differential equation approach, because we will use this in the buckling of beams. But right now, we have a good example to actually show them, versus the fourth order differential equation approach. Now start with the second order differential equation approach. Start with this one. We already solved this problem before. By what? By just take the Euler's beam or Euler's column. Actually, it's called Euler's column. Take Euler's column as an example. You have this problem and you apply the force P acting here. If you see the simply supported column subjected to a axial force, and this is what we call Euler's column. By the way. We already found that in order to find the buckling load, what we did was to establish the boundary, establish the reference coordinate system from one end, and usually we start from the bottom one. And to do so, you have the reference coordinate system y and x established, and then you take the free body diagram. Some were coming like this, right? And when we do that, our free body diagram looks like this.